Hi class, this is your instructor, Skylar Huff. We're now in Chapter 57, The Biosphere and Human Impacts. The biosphere includes all living communities on Earth, from the profusion of life in the tropical rainforests to the platonic communities in the world's oceans, and in a very general sense, the distribution of life on Earth reflects variations in the world's abiotic environments, such as variations in temperature and availability of water from one terrestrial environment to another. So as you're looking right here at the figure, it is a satellite image of the Americas. The colors are key to the relative abundance of chlorophyll, an indicator of the richness of biological communities. Green and dark green areas on land are areas with high primary productivity, such as thriving forests, whereas yellow areas include the deserts of the Americas and the tundra of the far north, which have lower productivity. Similarly, light blue areas along the coast are highly productive as the result of nutrient-rich upwelling currents, whereas pink areas are the least productive areas in the ocean. The global patterns of life on Earth are heavily influenced by the total amount of solar radiation that reaches different parts of Earth and seasonal variations in that radiation. And two, the patterns of global atmospheric circulation and the resulting patterns of oceanic circulation. Local characteristics such as soil types and the altitude of the land interact with the global patterns in sunlight, winds, and water currents to determine the conditions under which life exists and thus the distributions of ecosystems. The Earth receives energy from the sun at a high rate in the form of electromagnetic radiation at visible and near visible wavelengths. Each square meter of the upper atmosphere receives about 1,400 joules per second, which is equivalent to the output of 14 100-watt light bulbs. As the solar radiant energy passes through the atmosphere, its intensity and wavelength composition are modified. About half of the energy is absorbed within the atmosphere and half reaches the Earth's surface. The gases in the atmosphere absorb some wavelengths strongly while allowing other wavelengths to pass freely through. As a result, the wavelength composition of the solar energy that reaches the Earth's surface is different from that emitted by the sun. For example, the band of ultraviolet or UV rays known as UVB is strongly absorbed by ozone in the atmosphere, and thus this wavelength is greatly reduced by the solar energy that reaches the Earth's surface. Some parts of Earth's surface receive more energy than other parts, and this has a great effect on climate and life. So the tropics are particularly warm because the sun's rays arrive almost perpendicular to the surface of the Earth in regions near the equator. Closer to the poles, the angle at which the sun's rays strike, called the angle of incidence, spreads the solar energy out over more of the Earth's surface, providing less energy per unit of surface. And that's what you're seeing here in figure 57.1a. Earth's annual orbit around the sun and its daily rotation on its own axis are also important in determining patterns of solar radiation and their effects on climate. So because the axis is tilted by approximately 23.5 degrees, a progression of seasons occurs on all parts of the Earth, especially at latitudes far from the equator. The northern hemisphere, for example, tilts toward the sun during some months, but away during others, giving rise to summer and winter. The farther away from the equator, the greater the difference between summer and winter, as you see here being shown to you now. And this shows what I mentioned moments ago about that annual mean temperature as it varies with latitude. So you look at this figure and infer where you would find the tropical rainforest by that lack of variation in monthly mean temperature Celsius. The Coriolis effect. So the curvature of the paths of winds due to Earth's rotation. So in the northern hemisphere, it's counterclockwise. So winds curve to the right of their direct motion. Whereas in the southern hemisphere, winds curve to the left and they blow westward as well as toward the equator. So the reason for those wind patterns is that the circumference of a sphere, the Earth changes with latitude. The environmental conditions at a particular place are affected by regional and local effects of solar radiation, air circulation, and water circulation, not just the global patterns of these processes. So let's look at an example. Rain shadows is the first of which. Deserts sometimes occur because mountain ranges intercept moisture-laden winds from the sea. When the air flowing landward from the oceans encounters a mountain range, such as you see here, the air rises and its moisture holding capacity decreases because it becomes cooler at higher altitude, causing precipitation to fall on the mountain slopes facing the sea. As the air, stripped of much of its moisture, then descends on the other side of the mountain range, it is warmed and its moisture holding capacity increases, meaning it can readily take up moisture from the soils and plants. One consequence is that the two slopes of a mountain range often differ dramatically in how moist they are. In California, for example, the eastern slopes of the Sierra Nevada mountains facing away from the Pacific Ocean are far drier than the western slopes. Another consequence is that a desert may develop on the dry side, the Mojave Desert being an example. The mountains are said to produce a rain shadow, known as the rain shadow effect. Elevation. So temperature and other conditions, they do change with elevation. Air temperature falls about 6 degrees Celsius for every 1,000 meter increase in elevation. And you can see the difference not only in temperature, but you also see the difference in the composition of flora as elevation increases. So from sea level with a tropical rainforest, going farther up in elevation, the temperate forests, the taiga, tundra, and then polar ice. Microclimates. Conditions also vary in significant ways on a very small spatial scale. For example, in a forest, a bird sitting in an open patch may experience intense solar radiation, a high air temperature, and low humidity, even while a mouse hiding under a log 5 meters away may experience shade, a cool temperature, and air saturated with water vapor support. Such high localized sets of climatic conditions are called microclimates. Biomes are major types of ecosystems on land. Each biome has a characteristic appearance and is distributed over wide areas of land, defined largely by sets of regional climatic conditions. Biomes are named according to their vegetational structures, but they also include the animals that are present. As you might imagine, from the broad definition given for biomes, there are a number of ways to classify terrestrial ecosystems into biomes. Here we recognize 8 principal biomes: the tropical rainforest, savanna, desert, temperate grassland, temperate deciduous forest, temperate evergreen forest, the taiga, and tundra. 6 additional biomes recognized by some ecologists are polar ice, mountain zone, chaparral, warm, moist evergreen forests, tropical monsoon forests, and semi-desert. Other ecologists lump these 6 into the 8 major biomes, such as you see here. So this shows all 14 biomes. Biomes are defined by their characteristic vegetational structures and associated climatic conditions, rather than by presence of particular plant species. Two regions assigned to the same biome thus may differ in the species that dominate the landscape. Tropical rainforests around the world, for example, are all composed of tall, lushly vegetated trees. But the tree species that dominate the South American tropical rainforest are different from those in the Indonesian one. The similarity between such forests result from convergent evolution. In determining which biomes are found where, two key environmental factors are temperature and moisture. As seen in the figure before you now, figure 57.8, if you know the mean annual temperature and mean annual precipitation in a terrestrial region, you often can predict the biome that dominates. Temperature and moisture affect ecosystems in a number of ways. One reason they are so influential is that primary productivity is strongly correlated with them, as described in the last chapter. Different places that are similar in mean annual temperature and precipitation sometimes support different biomes, indicating that temperature and moisture are not the only factors that can be important. Soil structure and mineral composition are among other factors that can be influential. The biome that is present may also depend on whether the conditions of temperature and precipitation are strongly seasonal or relatively constant. So you're seeing here that difference. Tropical rainforests typically receive 140 to 450 centimeters of rain per year, and they are the richest ecosystems on land. They are very productive because they enjoy the advantages of both high temperature and high precipitation. They also exhibit very high biodiversity, being home to at least half of all species of terrestrial plants and animals in the world. That's over 2 million species, you all. In a single square mile of Brazilian rainforest, there can be 1,200 species of butterflies, twice the number found in all of North America. Tropical rainforests recycle nutrients rapidly, so their soils often lack great reservoirs of nutrients. Savannas are tropical or subtropical grasslands, often dotted with widely spaced trees or shrubs. On a global scale, savannas often occur as transitional ecosystems between tropical rainforests and deserts. They are characteristic of warm places where annual rainfall, 50 to 125 centimeters, is too little to support rainforests, but not so little as to produce desert conditions. Rainfall is highly seasonal in savannas. The Serengeti ecosystem in East Africa is probably the world's most famous example of the savanna biome. In most of the Serengeti, no rain falls for many months of the year, but during other months, rain is abundant. The huge herds of grazing animals in the ecosystem respond to the seasonality of rain. A number of species migrate away from permanently flowing rivers only during the months when rain falls. Deserts are dry places where rain is sparse. The annual rainfall is often less than 25 to 40 centimeters and unpredictable. The unpredictability means that in some places, plants and animals cannot depend on experiencing rain even once a year. As mentioned before, many of the largest deserts occur at latitudes near 30 degrees north and 30 degrees south because of the global air circulation patterns. Other deserts result from rain shadows. Vegetation is sparse in deserts, and survival of both plants and animals depend on water conservation. Many desert organisms enter inactive stages during rainless periods. To avoid extreme temperatures, small desert vertebrates often live in deep, cool, and sometimes even somewhat moist burrows. Some emerge only at night. Among large desert animals, camels drink large quantities of water when it's available, and then conserve it so well that they can survive for weeks without drinking. Oryxes, which are large desert-dwelling antelopes, survive opportunistically on moisture on leaves or roots that they dig up, as well as drinking water when possible. Halfway between the equator and the poles are temperate regions where temperate grasslands grow. These grasslands, also called prairies, once covered much of the interior of North America, and they were widespread in Eurasia and South America as well. The roots of perennial grasses characteristically penetrate far into the soil, and grassland soils tend to be deep and fertile. Temperate grasslands are often highly productive when converted to agricultural use, and vast areas have been transitioned in this way. In North America, prior to this change in land use, huge herds of bison and pronghorn antelope inhabited the temperate grasslands, migrating seasonally as resources changed over the course of the year. Natural temperate grasslands are one of the biomes adapted to periodic fire, and therefore need fires to prosper. Mild but seasonal climates, meaning warm summers and cold winters, plus plentiful rains promote growth of temperate deciduous forests in the eastern United States, eastern Canada, and Eurasia. A deciduous tree is one that drops its leaves in the winter. Deer, bears, beavers, and raccoons are familiar animals of these forests. Temperate evergreen forests occur along coastlines with temperate climates, such as the northwest of the United States, and the dominant vegetation includes trees such as spruces, pines, and redwoods that do not drop their leaves, thus they are evergreen. Taiga and tundra differ from other biomes in that both stretch in great unbroken circles around the entire globe. The taiga consists of a great band of northern forests dominated by coniferous forests, which include spruce, hemlock, and fir, that retain their needle-like leaves all year long. The taiga is one of the largest biomes on Earth. Winters in taiga regions are severely long and cold, and most of the limited precipitation falls in the summer. Many large herbivores, including elk, moose, deer, plus carnivores such as wolves, bears, and the lynx, and wolverines, are characteristic of the taiga. In the far north, at latitudes above the taiga, but south of the polar ice, few trees grow. The landscape that occurs in this band, called the tundra, is open, wind-swept, and often boggy. This enormous biome covers 1/5 of Earth's land surface. Little rain or snow falls. Permafrost, soil ice that persists throughout all seasons, usually exists within a meter of the ground surface. The few trees that occur in the tundra are small and mostly confined to the margins of streams and lakes. Large grazing mammals include musk oxen and reindeer, otherwise called caribou, and carnivores such as wolves, foxes, and lynx live in the tundra. Populations of lemmings, which is a small rodent native to the Arctic, rise and fall dramatically, with important consequences for animals that prey upon them. Of the major habitats, freshwater covers by far the smallest percentage of Earth's surface. Only 2% compared to 27% for land and 71% for ocean. The formation of fresh water starts with the evaporation of water into the atmosphere, which removes most dissolved constituents, much as distillation does. When the water falls back to Earth's surface as rain or snow, it arrives in an almost pure state, although it may have picked up biologically significant dissolved or particulate matter from the atmosphere. Freshwater wetlands, which include marshes, swamps, and bogs, represent intermediate habitats between the freshwater and terrestrial rims. Wetlands are highly productive. They also play key additional roles, such as acting as water storage basins that moderate flooding. Primary production in freshwater bodies is carried out by single-celled algae, referred to as phytoplankton, flowing in the water, by algae growing as films on the bottom, and by rooted plants such as water lilies. In addition, a considerable amount of organic matter, such as dead leaves, enters some bodies of water from plant communities growing on the land nearby. The concentration of dissolved oxygen is a major determinant of the properties of freshwater communities. Oxygen dissolves in water just as sugar does. Fish and other aquatic organisms obtain the oxygen they need by taking it up from solution. The solubility of oxygen is therefore critically important. In reality, oxygen is not very soluble in water. Consequently, even when fresh water is fully aerated and at equilibrium with the atmosphere, the amount of oxygen it contains per liter is at most 5% of that in air. This means that in terms of acquiring the oxygen they need, freshwater organisms have a far smaller margin of safety than breathing ones. Oxygen is constantly added to and removed from any body of fresh water. Oxygen is added by photosynthesis and by aeration from the atmosphere, and it is removed by animals and other heterotrophs. If a lot of decaying organic matter is present in a body of water, the oxygen demand of the decay microbes can be high, sometimes depleting the amount of oxygen available for other species. Under conditions in which the rate of oxygen removal from water exceeds the rate of addition to it, the concentration of dissolved oxygen can fall so low that many aquatic animals cannot survive. Bodies of relatively still fresh water are called lakes. If large and small, ponds if small. So I'll say again, those bodies of water that are still fresh water, they're called lakes if they're large, and ponds if they're small. Water absorbs light passing through. As a result, the intensity of sunlight available for photosynthesis decreases sharply with increasing depth. In deep lakes, only water relatively near the surface receives enough light for phytoplankton to exhibit a positive net primary productivity. Those waters describe the photic zone, shown here. The thickness of the photic zone also depends on how much particulate matter is in the water, also referring to its turbidity. Water that is relatively clear and relatively free of particulate matter allows light to penetrate to a depth of 10 meters at sufficient intensity to support phytoplankton. Water that is thick with surface algal cells or soil from erosion may not allow light to penetrate far before its intensity becomes too diminished for algal growth. The supply of dissolved oxygen to deep waters of lake can be a problem because oxygen enters aquatic systems near their surface, where gas exchange occurs with the air and photosynthesis occurs in aquatic organisms. In the still waters of a lake, mixing between the surface and deeper layers may not occur except occasionally as a result of thermostratification. So consequently, oxygen only rarely enters the deeper water from the surface waters. Thermostratification is a characteristic of many lakes and large ponds. So in summer, shown here, water warmed by the sun forms later known as the epipelinium at the surface. This is because warm water is less dense than cold water and tends to float on top. Colder, denser water, called the hypolimnium, lies below. Between the cold and warm layers is a transition layer, the thermocline. Although here we're focusing on fresh water, a similar thermal structuring of the water column also occurs in many parts of the ocean. So to make sure I go back just a bit, the photic zone is where light penetrates, as mentioned here, photic zone. And I will say that the littoral zone is that most productive zone of a lake or pond. And then the littoral zone, as mentioned, is going to be right there at the edge. And then the benthic zone or the aphotic zone is below the light penetration level, where no light can penetrate and it is dark. Briefly, bodies of fresh water that are low in algal nutrients and low in the amount of algal material per unit of volume are termed oligotrophic. Such waters are often crystal clear. Oligotrophic streams and rivers tend to be high in dissolved oxygen because the movement of flowing water aerates them. Excuse me. Eutrophic bodies of water are high in algal nutrients and often populate densely with algae. They are more likely to be low in dissolved oxygen, especially in summer. In a eutrophic body of water, decay microbes often place high demands on the oxygen availability because when thick populations of algae die, large amounts of organic matter are made available for decomposition. Human activities have often transformed oligotrophic lakes into eutrophic ones. For example, when people over-fertilize their lawns or fields, nitrate and phosphate from the fertilizers wash off into local water systems. Lakes that receive these nutrients become more eutrophic. About 71% of Earth's surface is covered by ocean. The continental shelves occur near the coastlines, where the water is not especially deep. The shelves, in essence, represent the submerged edges of the continents. Worldwide, the shelves average about 80 kilometers wide, and the depth of the water over them increases about 130 meters as one travels from the coast toward the open ocean. Beyond the continental shelves, the depth suddenly becomes much greater. The average depth of the ocean is 4,000 to 5,000 meters, and in some parts, called trenches, are far deeper, reaching 11,000 meters deep in the Marianas Trench in the western Pacific Ocean. In most of the ocean, the principal primary producers are phytoplankton floating in well-lit surface waters. A revolution is currently underway in scientific understanding of the limiting nutrients for ocean phytoplankton. Primary production by phytoplankton is presently understood to be the nitrogen limited in about 2/3 of the world ocean, but iron limited in about 1/3. So the world's oceans are so vast that they include many different types of ecosystem. Some, such as coral reefs and estuaries, are high in their net primary productivity per unit area, but others are low in productivity per unit areas. Ocean ecosystems are of 4 major types: open oceans, continental shelves, upwelling regions, and deep seas. Many of the ecosystems in the continental shelves are relatively high in productivity per unit area. An important reason is that waters over the shelves, termed neritic waters, tend to have relatively high concentrations of nitrate and other nutrients. Because the waters over the shelves are shallow, they have not been subject over eons of time to loss of nutrients into the deep sea as the oceans have. Over shelves, nutrient-rich materials that sink hit the shallow bottom, and the nutrients they contain are stirred back into the water column by stormy weather. In addition, nutrients are continually replenished by runoff from nearby land. And you can see that here. About 99% of the food people harvest from the ocean comes from the continental shelf ecosystems or by upwelling regions. The shelf ecosystems are also particularly important to humankind in other ways. Mineral resources taken from the ocean, such as petroleum, come almost exclusively from the shelves. In addition, almost all recreational uses of the ocean, from sailing to scuba diving, take place on shelves. The shelves feature prominently in these ways because they are close to coastlines and relatively shallow. Estuaries are one of the types of shelf ecosystems. An estuary is a place along a coastline, such as a bay, that is partially surrounded by land and in which fresh water from streams or rivers mixes with ocean water, creating brackish water or intermediate salinities. Estuaries, besides being bodies of water that include intertidal marshes or swamps, an intertidal habitat is an area that is exposed to air at low tide but underwater at high tide. The marshes of the intertidal zone are called salt marshes. Intertidal swamps are called mangrove swamps, dominated by trees or bushes, occur in tropical and subtropical parts of the world. Estuaries are a vital and highly productive ecosystem that provides shelter and food for many aquatic animals. Especially the larvae and the young that people harvest for food. Estuaries are also important to a very large number of other animal species, such as migrating birds. These are estuaries. Other types of shelf ecosystems include banks and coral reefs. Banks are shallow areas on shelves, often extremely important as fishing grounds. Georges Bank, about 100 kilometers offshore of Massachusetts, was formerly one of the most productive, but most of this area has been closed to fishing since the mid-1990s because of overexploitation. A coral reef is an ecosystem that occurs in subtropical and tropical latitudes. Their defining feature is that stony corals, or corals that secrete a solid, calcified type of skeleton, build three-dimensional frameworks that form unique habitat in which many other distinctive organisms live, including reef fish and soft corals. All of the 700 or so species of reef-building corals are animal-algal symbioses. The animals are cnidarians, and within the cells of the inner cell layer live dinoflagellate symbionts. These corals depend on photosynthesis by the algal symbionts and thus require clear waters through which sunlight can really penetrate. Reef-building corals are threatened worldwide. Upwelling regions of the ocean are localized places where deep water is drawn consistently to the surface because of the action of local forces such as local winds. The phenomenon named El Niño first came to the attention of science in studies of the South American upwelling region. In that region, every 2 to 7 years, an irregular and relatively unpredictable basis, the water along the coastline becomes very warm, and simultaneously the primary productivity becomes unusually low. The immediate cause of El Niño is a weakening of the east to west trade winds in the region. The trade winds ordinarily blow warm surface water to the west, away from South America, the South American coast. This thins the warm surface layer of water along the coast, so deep water, cold but highly enriched in nutrients, is drawn to the surface, leading to a high primary production. So weather systems of the western Pacific Ocean are shifted about 6,000 kilometers eastward because of the effects of El Niño, which may cause droughts in rainy areas, and areas that normally have little precipitation get soaked. So you may have heard of El Niño mentioned on the weather by way of the news. So this shows what happens by way of an El Nino winter. So if you live in the southeast United States, it says things are typically going to be wetter and cooler. Typically, wetter and cooler. We all know that human activities can cause adverse changes in ecosystems. In discussing these, it is important to recognize that creative people can often come up with rational solutions to such problems. An outstanding example is provided by the history of DDT in the United States. DDT is a highly effective insecticide that was sprayed widely in the decades following World War II, often on wetlands to control mosquitoes. During the years of heavy DDT use, populations of ospreys, bald eagles, and brown pelicans, all birds that catch large fish, plummeted. Ultimately, the use of DDT was connected with the demise of these birds. Scientists established that DDT and its metabolic products became more and more concentrated in the tissues of animals as the compounds were passed along food chains. Animals at the bottom of the food chains accumulated relatively low concentrations in their fatty tissues, but the primary carnivores that preyed on them accumulated higher concentrations from eating great numbers of prey, and the secondary carnivores that accumulated higher concentrations yet. Top-level carnivores, such as the birds that eat large fish, were dramatically affected by the DDT. In these birds, scientists found that metabolic products of DDT disrupted the formation of eggshells. The birds laid eggs with such thin shells that often they cracked before a young could hatch. Researchers concluded that the demise of the fish-eating birds could be reversed by a plan to clean ecosystems of DDT. And laws were passed banning its use. Now, over 4 decades later, populations of ospreys, eagles, and pelicans have rebounded dramatically. Freshwater is not just the smallest of the major habitats, but also the most threatened. One of the simplest yet most ominous threats to freshwater is that burgeoning human populations often extract excessive amounts of water from rivers, lakes, or streams. The Colorado River, for example, is one of the greatest rivers in North America, originating from snowmelt in the Rocky Mountains and flowing through Utah, Arizona, Nevada, California, and northern Mexico before emptying into the ocean. Today, water is pumped out of the river along its way to irrigate crops and to meet water needs of cities, even ones as distant as Los Angeles, California. The river now frequently runs out of water and dries up in the desert, never reaching the sea. Worldwide, many crises in the supply of fresh water loom on the horizon. Pollution of fresh water is a global problem. Point source pollution comes from an identifiable location, such as easily identified factories or other facilities that add pollutants at defined locations, such as an outflow pipe. Examples include sewage treatment plants, which discharge treated effluents at specific spots on rivers, and factories that sometimes discharge water contaminated with heavy metals or chemicals. Laws and technologies can readily be brought to bear to moderate point source pollution because exact locations and types of pollution are well defined. In many countries, great progress has been made, but in other countries, often in the developing world, water pollution is still a major problem. Diffuse pollution is exemplified by eutrophication caused by excessive runoff of nitrates and phosphates from lawn and agricultural field fertilization. When excessive nitrates and phosphates enter rivers and lakes, the character of the bodies of water is changed for the worse. The concentration of dissolved oxygen declines, and fish species such as carp take the place of more desirable species. The problem is exacerbated when rivers empty into the ocean. Eutrophication caused by the accumulation of chemicals can lead to enormous areas with no oxygen, causing massive die-offs of fish and other animals. The most famous such area, covering about 23,000 kilometers squared in 2017, an area the size of New Jersey, occurs where the Mississippi River empties into the Gulf of Mexico, but other dead zones occur in places around the world. The nitrates and phosphates that cause these problems originate on thousands of farms and lawns spread over whole watersheds. They often enter fresh waters at virtually countless locations. The diffuseness of this sort of pollution renders it difficult to modify by simple technical fixes. Instead, solutions often depend on public education and political action. So yes, from your lawn, from that farm or your farm, yes, from golf clubs, etc. Probably the single greatest problem for terrestrial habitats worldwide is deforestation by cutting or burning. There are many reasons for deforestation. In poverty-stricken countries, deforestation is often carried out diffusely by the general population. People burn wood to cook or stay warm, and they collect it from local forests. At the other extreme, corporations still cut large tracts of virgin forests in an industrialization fashion, often shipping the wood halfway around the world to buyers. Tropical hardwoods, such as mahogany from the Southeast Asian rainforests, are shipped to the United States for use in furniture. Softwood logs are shipped from Alaska to East Asia for pulping and paper production. Forests are sometimes simply burned to open up land for farming or ranching, and in recent years, increased demand for soybeans has been a particular culprit. Unfortunately, despite concerted efforts by environmental organizations and some countries, global rates of deforestation have risen in the last few years. The countries with highest rates of forest loss changed over time. In the early 2020s, Brazil suffered massive deforestation, but the rate there has declined more recently, even as it has increased in other countries such as Laos, Bolivia, and Nicaragua. In 2020, a massive forest fire occurred. The amount of forests burned in the western United States was greater than ever. California alone lost an area the size of Connecticut, and scientists are concerned that massive fires in the Amazon rainforest may reach a climatological tipping point. Reduced forest cover will change future rain patterns, thus converting the area permanently to grassland. Unfortunately, in these places and elsewhere, such as Indonesia, they are expected to worsen with increased global warming. And from 2019 to 2020, Australia lost 20% of its forests and 1 billion vertebrates. This was called, or at least occurred during what is known as Black Summer fires. It burned uncontrolled for months. So you're seeing a picture of the western coast of Madagascar taken from space. The land appears reddish-brown because the forest has been cleared, leaving Madagascar's characteristic red soil. The rivers run brown after heavy rains because of high levels of soil erosion. The blue color at the bottom is the ocean, and note how brown the water is where the river discharges into the sea. The loss of forest habitat can have dire consequences. Tropical rainforests are the biologically richest terrestrial habitats in the world. Thus, when rainforests are cleared, the loss of biodiversity can be extreme. Many tropical forest regions have been severely degraded, and recent estimates suggest that less than half of the world's tropical rainforests remain in pristine condition. All of the world's tropical rainforests will be degraded or gone in about 30 years at present rates of destruction. Besides loss of habitat, deforestation can have numerous secondary consequences depending on local contexts. In the Sahel region of the Sahara Desert in Africa, deforestation has been a major contributing factor in the increased desertification in the forests of northeastern United States. As the Brook experiment shows, deforestation can lead to both loss of nutrients from forest soils and simultaneous nutrient enrichment of bodies of water downstream. And this also disrupts the water cycle. Contagious diseases that spread between animals and humans. The interactions with forests and its inhabitants are leading to an increase in new human health problems. Zoonotic diseases are contagious diseases that spread from animals to humans. Throughout our species' history, we have been the unhappy recipient of many such maladies. The plague, the flu, cholera, salmonella, and many more. 60% of all human pathogens are zoonotic in origin, but in recent years, a great number of new diseases have made the jump to humans, including the West Nile virus, hantavirus, the Middle Eastern Respiratory Syndrome, known as MERS, severe acute respiratory syndrome, SARS, Zika, and most recently COVID-19. Ebola is another zoonotic disease that has long been known, but erupted in 2014, killing more than 11,000 people in West Africa. There are a number of reasons for the recent occurrence of so many new zoonotic diseases, but many have resulted from humans increasingly using forests and coming into contact with their inhabitants that harbor disease organisms. Human immunodeficiency virus, HIV, was transmitted to humans from apes and monkeys in West Africa, very likely occurring when the animal's blood entered a human during hunting or butchering. Zoonotic diseases can also result when humans disrupt the forest ecosystem. A clear example is the outbreak of Lyme disease, which is diagnosed in 300,000 people in the United States every year, most of them in the northeastern states. This disease is caused by a bacterium, Borrelia burgdorferi, which is commonly found in white-footed mouse. And that's Borrelia burgdorferi. The bacterium is transmitted from one mouse to another by the blackleg tick, which can also transmit the disease to humans. So unfortunately, the conditions for the development of new zoonoses are becoming increasingly common, and new diseases keep emerging. For many years, epidemiologists were concerned that a disease that is easily transmissible between humans, for example, by contact or coughing, could cause a major epidemic. Just that probably happened in 2020 when a new airborne disease likely emerged from the wild animal wet markets of China, originating in bats and transmitted through a still undetermined intermediate species sold in that market. The COVID-19 virus made its jump to humans in late 2019 or early 2020, starting the largest human pandemic in a century. So effects of pollution on the ocean, there are many of those. So plastics found washed up on beaches in remote areas. Waters are now laced with toxic chemicals And a biopsy of the tissue of an Arctic killer whale revealed high levels of pesticide and even flame retardant chemicals. Not to mention microplastics are pervasive in the oceans, and they were detected in the human placenta in 2020. So, along with that, the ocean is also becoming a bit more acidic, and it's due to burning in other sources. So carbon dioxide ends up being dissolved in the ocean. So the biological consequences are still unclear at the moment. So estuaries have been subjected to severe eutrophication and then destruction of salt marshes. So a major contributing factor to hurricane destruction along the coast of Louisiana, and had marshes been present, Hurricane Katrina may not have caused so much damage. And to make this make a bit more sense, by destroying the salt marshes, which, like freshwater wetlands, are often perceived as disposable, most authorities believe that the loss of salt marshes in the 20th century was a major contributing factor to the destruction of New Orleans by Hurricane Katrina in 2005. Had those salt marshes and cypress swamps been present at their full extent, they would have absorbed a great deal of the flooding water and buffered the city from some of the storm's violence. The colors of the satellite photo in figure 5725A represent different concentrations of ozone located 20 to 25 kilometers above Earth's surface in the stratosphere. Stratospheric ozone is depleted over Antarctica, the purple region in the figure, to between 1/2 and 1/3 of its historically normal concentration, a phenomenon called the ozone hole. Although depletion of stratospheric ozone is most dramatic over Antarctica, it's a worldwide phenomenon. Over the United States, the ozone concentration has been reduced by about 4%, according to the United States Environmental Protection Agency, also referred to as being the EPA. Stratospheric ozone is important because it absorbs ultraviolet radiation, or UV radiation. Specifically, the wavelengths called UVB from incoming solar radiation. UVB is damaging to living organisms in a number of ways. For instance, it decreases risks of it increases incidence of cataracts and skin cancer in people. Depletion of stratospheric ozone permits more UVB to reach Earth's surface and increases the risks of UVB damage. Every 1% drop in stratospheric ozone is estimated to lead to a 6% increase in the incidence of cancer. For example, in the southern hemisphere, where ozone depletion is greatest, rates of skin cancer are much higher than elsewhere in the world. In Australia, for example, 2 out of every 3 people will develop skin cancer by age 70. Ultraviolet radiation exposure may also be detrimental to many types of animals, such as amphibians. The major cause of the depletion of stratospheric ozone is the addition of industrially produced chlorine and bromine-containing compounds to the atmosphere. Of particular concern are the chlorofluorocarbons, used until the 1990s as refrigerants in air conditioners and refrigerators, and in manufacturing. CFCs released into the atmosphere can ultimately liberate free chlorine atoms, which in the stratosphere catalyze the breakdown of ozone molecules to form ordinary oxygen. Ozone is continually made and broken down, and free chlorine atoms tilt the balance toward faster rate of breakdown. By studying the Earth's history and making comparisons with other planets, scientists have determined that concentrations of gases in our atmosphere, particularly CO2, maintain the average temperature on Earth about 25 degrees Celsius higher than it would be if these gases were absent. This fact emphasizes that the composition of our atmosphere is a key consideration for life on Earth. Unfortunately, human activities are now changing the composition of the atmosphere in ways most authorities conclude will be damaging or, in the long run, disastrous. Because of the changes in atmospheric composition, the average temperature of the Earth's surface is increasing, a phenomenon called global warming. As you might imagine, from what was said at the beginning of this chapter, changes in temperature alter global wind and water current patterns in complicated ways. This means that as the average global temperature increases, some particular regions of the world warm to a lesser extent, whereas other regions heat up to a greater extent. It also means that rainfall patterns are altered because global precipitation patterns depend on global wind patterns. Enormous computer models are used to calculate the effects predicted in all parts of the world. So as you can see here, these are anomalies in surface temperature in degrees Celsius for June of 2023. To the right, the rate of temperature change from 1900 to 2020. Based on a variety of different scenarios, computer models predict that global temperatures will increase 2.1 degrees Celsius to 5.7 degrees Celsius by the end of this century. That's roughly 3.8 to 10.3 degrees Fahrenheit. More ominous, perhaps, than temperature are some of the predictions for precipitation. For example, although Northern Europe is expected to receive more precipitation than today, another recent study predicted that parts of Southern Europe will receive about 20% less, disrupting natural ecosystems, agriculture, and human water supplies. Some European countries may come out ahead economically, but others will come out behind, and political relationships among countries will likely change as some shift from being food exporters to being more tenuous role of requiring food imports. Carbon dioxide is the gas usually emphasized in discussing the cause of global warming. If you look at figure 5728 shown here, although other atmospheric gases are involved, a monitoring station at the top of the Mauna Loa volcano on the island of Hawaii has monitored the concentration of atmospheric CO2 since the 1950s. This station is particularly important because it is in the middle of the Pacific Ocean, far from the great continental land masses where most people live, and it is therefore able to monitor the state of the global atmosphere without confounding influences of local events. In 1958, the atmosphere was 0.031% carbon dioxide. By 2023, the concentration had risen to 0.042, the highest it has been in the last 2 million years. All authorities agree that the cause of this steady rise in atmospheric CO2 is burning of coal and petroleum products by increasing and increasingly energy-demanding human population. The atmospheric concentration of CO2 affects global temperature because carbon dioxide strongly absorbs electromagnetic radiant energy at some of the wavelengths that are critical for the global heat budget. The Earth not only receives radiant energy from the sun, but it also emits radiant energy into outer space. The Earth's temperature will be constant only if the rates of these two processes are equal. The incoming solar radiation is relatively short wavelengths of the electromagnetic spectrum, wavelengths that are visible or nearly visible. The outgoing energy from the Earth is at different longer wavelengths. Carbon dioxide absorbs energy at certain of the important long wave infrared wavelengths. This means that although carbon dioxide does not interfere with the arrival of radiant energy at short wavelengths, it retards the rate at which energy travels away from the Earth at long wavelengths into outer space. CO2, carbon dioxide, is often called a greenhouse gas because its effects are analogous to those of a greenhouse. The reason that a glass greenhouse gets warm inside is that the window glass is transparent to light, but only slightly transparent to long-wave infrared radiation. The energy that strikes the greenhouse as light enters the greenhouse freely. Once inside, the energy is absorbed as heat, then re-radiated as long-wave infrared radiation. The infrared radiation cannot easily get out of the glass, and therefore, energy accumulates inside. Other greenhouse gases include methane and even nitrous oxide. The effect of any particular greenhouse gas depends on its molecular properties and concentration. For example, the molecule methane has about 20 times the heat trapping effect of carbon dioxide. On the other hand, methane is less concentrated and less long-lived in the atmosphere than carbon dioxide. Agricultural use of fertilizers is the largest source of nitrous oxide emissions, with energy consumption second and the industrial use third. Evidence for global warming can be seen in many ways. For example, on the worldwide statistical basis, ice on lakes and rivers forms later and melts sooner than it used to. On average, ice-free seasons are now 2.5 weeks longer than they were a century ago. Also, the extent of ice at the North Pole has decreased substantially, and glaciers are retreating around the world. If you look closely, Mount Kilimanjaro in Tanzania in 1970 is shown here at the top, and in 2014 at the bottom. Note the decrease in glacier coverage over 4 decades. Global warming and cooling have occurred in the past, most recently during the ice ages and the intervening warm periods. Species often responded by shifting their geographic ranges, tracking their environments, and for example, a number of cold-adapted North American tree species that are now found only in the far north or at higher elevations live much farther south at substantially lower elevations, 10,000 to 20,000 years ago, when conditions were colder. So present-day global warming is having similar effects. So you're seeing the distribution of the speckled wood butterfly, and you see how its range has shifted. The distribution here in Great Britain from 1995 to 2009 in teal, and include areas as far north from 1915 to 1939 in the olive green. Plants are flowering earlier. Since the year 812, people in Japan have recorded when the cherry trees flower in Kyoto, Japan. Most of the increase has occurred in the last 170 years, during the time which the average has moved earlier and earlier in the year by 12 days, as indicated by the red line, which is the average flowering date for the preceding 30 years. The year 2021 was the earliest recorded flowering date in the 1,209 years since recording began. The earlier flowering results from both increasing global temperatures and increased temperature in the cities, the heat island effect, which results because cities have more heat-absorbing surfaces, such as concrete, and fewer trees. On pause for possible effects on human populations. Rising sea levels, 200 million people, would be affected by increased flooding, and coastal cities and entire islands could be submerged. So increasingly frequent storms, flooding, and drought will have adverse consequences on human health, aside from their direct effect, such events often disrupt the fragile infrastructure of developing countries, leading to the loss of safe drinking water and other problems. As a result, epidemics of cholera and other diseases may be expected to occur more often. Rainfall changes in rainfall patterns, temperature, pest distributions, and other various factors will require many adjustments in agriculture. Such changes may come relatively easy for farmers in the developed world, but the associated costs may be devastating for those in the developing countries. So this has been your instructor, Skylar Huff.